A foundation settlement, or a landslide, or a tunnel collapse means that particles are moving. Displacement is 1/2 acceleration delta t squared, and acceleration is coming from Newton, F equal ma. That means that if there was a displacement, there was an unbalanced force. Then we have to ask, what are the forces that are acting on particles? So let's build this list of forces together, and we will then compare them to see when are some of them more important than others. Here we go. Obviously, the first and most important characteristic of a particle is its mass. And so the force due to mass is the weight, which is equal to, we could think of a cubic particle or a spherical particle. Let's do it for a cubic particle. So then it will be the size d cubed times the mass density of the mineral times gravity. If a particle is going to accelerate, there will be an inertial response, and that force is going to be equal to mass times acceleration, which is the same mass as the one that determines the weight of the particle. However, the acceleration is going to be the one that is triggering this inertial reaction. Finally, and of the same nature, is the buoyant force. When a particle is submerged, Archimedes told us that the buoyant force that the particle will experience is equal to the weight of the displaced fluid. Now, the displaced fluid is the volume, which is d cubed, times the weight of the fluid, which will be raw water, times g, the unit weight of the fluid. As you can see, these three forces are determined by the volume. They are volumetric in nature, and therefore they scale with the scale of the particle to the cube, to the volume. A particle, for being part of a skeleton, and let's assume that the granular skeleton is like a simple cubic packing, it has to contribute to load carrying. So if at the top I apply an effective stress sigma, then how much load is each particle carrying? Well, whether it is a spherical particle or a cubic particle as we have selected here, the particle has to carry not only its cross-sectional area, but the effective contribution area between particles. Like a column carries not only the load immediately above it, but the contribution area that loads onto the column. So we're going to call this force the force the particle must carry for being part of a granular skeleton. We're going to call it the skeletonian force, and it's going to scale with the cross-sectional area of the particle and its contribution area times the effective stress. So now we see that this one is now proportional to the square of the particle size. Particles in a soil mass often experience some form of diagenesis and cementation. So, for example, a particle could have some sediment precipitation at the contact, and that can have a tremendous implication on the stiffness and the strength and the dilatancy and the hydraulic conductivity of this material, with very early and minor cementation that most often goes undetected, but we should actually pay close attention to it. And so this cementation force will be proportional to the area that the cement occupies, which probably is in the same order of magnitude, will be correlated by the mass fraction of the particles, but we are going to make it related to d square and the adhesive strength of the cement, or the tensile strength of the cement. Notice that this force is not an active force, in the sense that these are continuously being felt by the grain. However, this one will only get activated if I try to deform the granular skeleton. So it's a passive force. There are also forces that are induced by thermal changes. So let's look at this thermal force. And a simple analysis would be similar to when we have a beam supporting a temporary excavation. So if you look at the beam here and the sun shines, this beam will experience a delta T, and because of that delta T wants to expand, and the deformation will be equal to alpha delta T is the strain times the length of the beam. Now that is going to create a reaction force from the soil, from the walls, which is going to be which would by itself cause an elastic deformation. This is the thermal deformation, which is going to be strain times L. Now the strain is equal to stress over Young's modulus times L, and stress is going to be the force N over the area times the Young's modulus times L. Now by superposition, and this presumes linearity, but by superposition we are going to say, what about if we create zero lateral strain conditions, zero lateral deformation? In that case, the thermal deformation that the material wants to experience is going to be totally compensated by the compressive strain that the boundary will create on the beam. And so then we can conclude that when delta due to temperature is equal to delta due to elasticity, then the L and the L's will cancel out, and N will be equal to the force N, now that the material is experiencing, is going to be equal to EA times alpha delta T. Notice that we need to keep careful sense of what is happening here. In the granular material, the E that we're talking about is the E of the stiffness of the skeleton. The thermal expansion coefficient is the one that corresponds to the skeleton, and the area is the per unit area of a particle size. And so this is going to be of the order of d square E alpha delta T. Once again, this is another d square relationship. The next series of forces are going to be related to water. Of course, that was also the case of buoyancy, but now the water is going to be moving relative to the particle. We know, for example, that when somebody jumps with a parachute, that was Leonardo's idea, then at the beginning is going to accelerate because there is only one acting force, which is the self-weight. But then as the velocity increases, drag begins to act, and eventually the self-weight and the drag force become the same. There is no more unbalanced force, and the parachuter reaches terminal velocity. This is the type of ideas behind Stokes' law, and what we're looking for now is the drag force that participates in this analysis. So the drag force is going to be proportional to the viscosity of the fluid, to the relative velocity between the particle and the fluid, whether the particle is static and fluid is moving through the pores in soil matter, or a particle is flowing and falling through a jar filled with water. It's the relative velocity that matters. But then there will be factors related to size and shape. For the case of a sphere, this is 3 pi and the diameter. And I highlight that this is linearly proportional to the length scale of the particle. This is when the particle is moving relative, once again, to the water and creates streams like that. But there is one more situation that develops here, whether the particle is resting on the surface of another grain or a rock mass in the case of a fracture, or there are two particles in the medium. Now the flow lines are different, and they create like a wing effect that lifts the particles, and that causes the saltation of particle migration. And when these two particles are at some separation, actually it causes the attraction between these particles. So there is another hydrodynamic force, which is this attraction or this lift force that occurs under those situations. So there is a hydrodynamic force of some kind that is also acting. Depending on the processes, it may gain some relevance. The presence of water creates very important set of forces that give rise to unsaturated soil behavior. Let's consider the following situation. We have a soil packing submerged, and then evaporation takes place and the water gradually gets closer and closer to the surface, and by the time it gets on the surface of the grains, the water likes the grain. In most cases, the grains are hydrophilic, and it hugs the grains, and now the water is underneath. It has already dropped, and the water really doesn't want to invade anymore because it's hanging from the particles. And so it's hanging from the particles because there is an interfacial tension and a contact angle between the particle and the water. In the extreme case where that contact angle is 0, the forces are vertical, and we can have an estimation of the capillary force. We're going to call it Cp, the capillary force, which is going to be of the order of that interfacial tension, which we're going to call Ts, and it's acting all around the perimeter. So it's 2 pi r, and therefore we're going to cancel the 2 and put a d to estimate the force. Pi surface tension diameter. There are other situations that may emerge, and sometimes particles get greasy. They're hydrophobic, and we can purposely do that. For example, we do that to do mineral separation in the mining industry. We make the particles hydrophobic, and then we bubble air, and because particles hate the water, as soon as they see an air bubble, they will go and grab the air bubble and will float with it, a technique called flotation for mineral separation. So the same will happen here. If these two particles are submerging water and they are hydrophobic, they prefer to be close together because they hate everybody else that surrounds them. And so that what will happen is that they will come like that, and there will actually be a normal compressive force between them because of hydrophobic interaction with the medium. And that technique is very useful for many applications. For example, we can put hydrophobic particles flowing inside the pores of the soil, particle-laden fluids, so that when they find a surface that they like more than the mineral surface of the soil or the water, they will stick to that interface. For example, this could be hydrophobic nanoparticles or organobentonites, and they will preferentially accumulate near oil interfaces or D-NAPOLs and L-NAPOL contaminants, and we can use them for environmental remediation or for enhanced oil recovery. The next set of forces are of electrical nature. We will soon see that electrical interactions do not affect large-scale particles, but they become very important for small-scale particles. That means when we go below the 10 micron, the 1 micron size, which happens to be all clays and clayey materials, which are everywhere in nature. One of those forces is van der Waals attraction. And this one will take us a little bit to explain, but here we go. Clearly, if you have a cation and an anion, there is attraction. And if you have a cation and let's say a dipolar molecule like water, then the cation will attract the oxygen, will repel the hydrogens, and will cause the molecular to rotate. So if we see that an instant later, this is the situation with that molecule. But now here happens something that is quite interesting, that if you look at the Coulombian force, F equal Q over R square, 1, 2, 1, 2, 1 over 4 pi epsilon 0, that force is inversely proportional to the distance squared. That means that even though this is charge 2 and here I have 2 times 1, the attraction to the oxygen is much greater than the sum of the two repulsions to the hydrogen. Therefore, a positive charge will have attraction to polar molecule, electrically neutral, and the same will happen with a negative charge. Now, if the two molecules were non-polar, like we could think of the simplest case of atoms, hydrogen atoms with one electron rotating around, when the electrons come together, there is very pronounced repulsion, so they begin to rotate in synchronicity in the way that they are always far away from each other. But if at that moment you see the positive charge, the negative electron, the positive proton, the negative electron, and that particular instant, you realize that there is attraction. And so a polar molecule polarizes a non-polar molecule. A charge polarizes and creates orientational polarization of non-polar molecules and dipoles. And now we have a whole sequence of situations, and in the end, you convince yourself that in case of doubt, nature likes attraction. And this gives rise, this which is happening at molecular, atomic and molecular scale, integrates now when we have two particles across a water film or a fluid film, and all these processes of orientation and mutual polarization takes place, rendering the system overall attractive. This is the attraction force between two platy particles. So imagine now that I have two platy particles at a distance h between them and of size d, length scale d. Then there is an attraction force that is going to be proportional to a parameter which we are going to call the Hamaker constant, AH, and the square. But it is very sensitive to the interparticle separation. So this will be very sensitive to H goes to the cube, and there may be another number, a factor here, let's say 24 for this equation. So this is the attraction force between two platy particles parallel to each other coming in close proximity. As you realize, the effect really accelerates as the distance between the particles becomes very small. This is van der Waals attraction force. There are two important electrical interaction forces: the van der Waals attraction force between particles and the double layer repulsion. This Hamaker constant, you're going to find in some manuscripts that it can be estimated using what is called the Lifshitz simplified theory, which basically takes into consideration the permittivity or dielectric constant of the interacting minerals and the fluid in between. What is very important to realize that is inversely proportional to the separation between particles to the cube. The double layer repulsion force is also scaling with the exposed areas that are interacting, d square, and it is a more complex function of hyperbolic cosines and cosecants, which are a function of the distance between the particles, h, the separation between particles, and the thickness of the double layer. So go back to other lectures where we talk about mineral-liquid interaction to understand what is that quantity, but it's the thickness of that counter ion cloud that is compensating the surface charge of minerals, in particular clay minerals. When we superimpose these two forces together, we have something that is called the DLVO theory, which are the initials for the four scientists that developed the theory. And when I plot them, it looks something as follows. Here I put the separation between particles h, and let's say that at the top repulsion prevails, at the bottom attraction prevails. If the ionic concentration and the valence, that means the ionic strength, is high, the thickness of the double layer is small, double layer repulsion vanishes and is all controlled by the attraction force. So this is when the concentration times the valence square is high. Conversely, if the concentration and valence are low, the thickness of the double layers are wide, there is lots of interaction between the electrostatic potentials and repulsion prevails. That is true until the particles come sufficiently close enough that this h cube in the denominator takes over and attraction prevails. And so this is the trend for what we have just described. This is when the ionic strength concentration valence square is low. Notice that if I push particles dynamically by steering, by mixing, and I push them to overcome this repulsion barrier, particles may indeed aggregate, which would not happen under quiescent conditions where they would never come close and overcome the repulsion barrier. What I'm just describing here is probably taking place in a scale of, let's say, the closest 10 nanometers to the particle surface. And 10 nanometers is nothing for sands because the asperity is probably 3-4 orders of magnitude larger than 10 nanometers. Asperities will be in the order of several microns. However, this gains tremendous importance when the particles are very thin. Remember that montmorillonite, the particle thickness is 9.6 angstroms, and so 10 nanometers is actually much greater than the particle thickness. So everything becomes controlled by this type of phenomena. Now you may wonder what happens when these forces are, particles are very close to each other. Well, when particles are very close to each other, two other processes take place. To explain it, think of a large plate on top of marbles. thick marbles, and there is a rigid base at the bottom. When there are a large number of layers of marbles between the two, then as you push the plate down, marbles really flow out, and we have a typical bearing capacity situation. But as you come closer and closer, now you have to push. Now let's say that the plate is in this position. Now you have to push a layer out and squeeze it out all together. So you will begin experiencing like a jerky motion that you push, 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 and slide of particles gets out. And then you push harder, 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 slide gets out. And so in this very narrow region, if I expand it, you're going to see that the forces begin repulsion, and then that is the solvation force. Solvation. And it is because now the interparticle distance is such that you actually see the particles themselves, and you experience particulate nature of fluids at the molecular scale. This is actually measurable, and a device developed by Jacob Israel-Leville is a classical one to study how two curved mica plates begin to experience these oscillating forces. Now, what happens all the way at the end? Well, all the way at the end, they have come so close that you are interacting mineral to mineral surface, but at that scale now, matter doesn't exist anymore. It's almost all vacuum, and it's all about experiencing electrical interactions and repulsion. And so the meaning of two solids in contact is difficult to grasp, because if we begin zooming in, a solid is really, most of it is vacuum, and it's all determined by electrical interactions. And so when that happens, when it is very close now, this force really kicks up, and this is called the Born repulsion, when you actually see the van der Waals radius of each atom. To summarize the electrical part, we have the van der Waals attraction, the double layer repulsion, solvation forces, and the Born repulsion when you have mineral to mineral contact. There is one more force that I would like to mention, because it may open quite unique opportunities, and that is a force that a ferromagnetic particle would experience approaching a magnetic pole. And so let's call that the magnetic force, and that magnetic force is proportional to the mass, so it's proportional to d cubed, and this is the magnetic permeability of free space. The susceptibility of the material to being magnetized by the applied field, this is the magnetization, times the gradient of the magnetic field. And while this may sound far-fetched, there is a possibility that we could inject a ferromagnetic fluid inside the material and then apply a magnetic field, an external magnetic field, to cause changes internally. And this could be in medicine to transport to specific locations chemicals to attack cancer, or this could be in the geotechnical field to fill in the pore space in the material, apply a magnetic field so the magnetorheological fluid locks in, and then we can carve the specimen, put it in a triaxial, confine it, remove the magnetic field, and take the fluid out to actually recover the sand with its full fabric. And this was an idea explored even in the 80s, both in Japan and at Purdue University. So there are interesting possibilities, and as we are creating more and more tunable granular materials, we have to be alert to all the possible forces, because they can all serve a purpose to control granular material behavior. As I come back, we are going to analyze how the balance between these forces is going to affect the response. But before I erase, I would like to highlight once again that these are to the cube, square. There are many others that are squared, like the electrical interactions. The magnetic one goes once again to the cube, and there are some of them that are linear. Meaning the following. For example, if I compare the skeletal force with the thermal force, if I do the ratio, that ratio to see who wins, the skeletal force or the thermoelastic force, means that the d squared cancels out. That means that thermoelastic effects are going to be important regardless of particle size, and their relevance is going to be determined only by the thermal expansion coefficient and the skeletal stiffness and the temperature change and the effective stress applied. Then we can also see that there may be a certain size for which the capillary force can be more important than even the self-weight. So we'll come back and compute that one. To summarize, we have some particle level forces that are proportional to d cubed. The mass, the volume prevails. Some forces are proportional to the square, the area, like electrical interaction forces. These ones were the gravimetric, the buoyancy, the self-weight. And then there are forces that are proportional to the diameter, such as the hydrodynamic force. So when we plot these forces in a log-log scale, then these are power functions, and so they become linear functions. So let's look at this. This is the diameter in logarithmic scale, and these are the forces in logarithmic scale. And we're going to have the 1-to-1 slopes, the 2-to-1, and the 3-to-1. What this means is that they are going to intersect. And if they intersect, they're going to determine a region where the force that is above prevails, or when otherwise where the other force prevails. So this map is a beautiful map to identify the different regimes of the forces that control soil behavior. Let's try to identify some of the transitions. For example, we can consider the capillary force, and the capillary force, remember, is the surface tension acting around the perimeter, which turns out to be pi d surface tension. And to cancel things out a little bit better, let's consider the weight of the particle, of a spherical particle, which is 4/3 pi r cubed, the volume, and then to convert to diameter, this becomes pi d cubed over 6 raw mineral times gravity. When these two forces are the same, which is the intersection point that we are looking at, when these two forces are the same, then the d with the d cube cancels out, and we get d squared, which will give us the square root of, and this will be the pi surface tension over, the pi will also cancel out, pi raw mineral g over 6 square root. The pi and the pi cancels out, and now the interfacial tension between air and water is 72 millinewtons per meter. So this is going to be 6 times 72 millinewtons is 10 to the minus 3 newtons and per meter. And the unit weight, this is the unit weight of the mineral, is 2,650 kilograms per cubic meter, which is 26.5 times 10 to the 3 newtons per meter cube, square root of. So let's cancel a few things here. This is millinewtons. This was a minus 3. So the 10 to the minus 3 with the 10 to the minus 3 in the numerator, minus 3 coming from the denominator is minus 6, goes out to minus 3, and the meter square goes out as a meter, and therefore this is going to be 10 to the minus 3 meters, which is in millimeters. And the only thing that we have left is 6 times 72 over 26. 72 over 26 is approximately 3 times 6, 18, and the square root of that is about 3 or 4. And so let's put 4 millimeters. And this is an upper estimate because we are assuming that that capillary force is acting all around the perimeter with 0 contact angle. And in fact, there could be smaller corrections. But this is giving us an idea of the transition between gravity and self-weight control behavior to capillarity control behavior. Therefore, if we have a scale of diameters, of particle diameters, and here is micrometer, and this is millimeter, then we can begin making some important assumptions or conclusions. Capillary forces begin gaining relevance with respect to self-weight when particles are smaller than a few millimeters. In other words, we cannot make sandcastles with particles coarser than a few millimeters. Now we can do similar analysis to identify other boundaries. For example, when does the Skeletonian force, the normal force N, which you may remember was sigma d squared, prevail? And then we can compare what about the electrical forces. The electrical forces gets a little bit trickier because there is this dimension of the interparticle separation that we need to take into consideration. But when you do the analysis, let me anticipate the following. I could compute the change in electrical forces due to changing water from fresh water to seawater for a soil buried 10 meters underground. And you will see that there is no effect, there are no volumetric changes for coarse particles, and that electrical forces gain relevance in this regime. And by the way, these capillary forces gaining relevance at large particles, that is true, but on the other hand, recognize that by the time I bury the particles, I have to compare that capillary force with the skeletal force. So then I will have another relationship, and we can try to extract that. So if I compare the capillary with the electrical force, then I will have that D at the transition is going to be equal to pi interfacial tension Ts over stress. So the higher the state of stress, the smaller the particles have to be for capillary suction to be relevant. And so this was the extreme case that we were competing with the self-weight of the particle, but really for a soil, let's say at 100 kilopascals, which may be 10, 15 meters for an unsaturated condition, then that soil will really have to be finer than the silt size to have the effect of capillarity. This type of analysis is very insightful, and it gives us the fundamental understanding, the foundations, for us to begin recognizing where couple processes become important. In other words, if we change the pore fluid chemistry, when does it become important? If we replace CO2 for brine for carbon geological storage, will it affect the seal capacity of shales? Will clays, silty soils contract when the suction changes during desiccation, etc., etc.? You can do it at the macro scale with empirically determined parameters for your soils, but you can always go back to the particle scale and understand what are the forces that are causing the particles to displace.